Alright, welcome back. So today we'll be doing question 22, generate parentheses. So given n pairs of parentheses, we want to write a function that generate all combinations of well-formed parentheses. Alright, so let's take a look at what they mean. So given a number like n equals to 3, right? They want us to generate 3 pairs of parentheses. And basically we want all the combination of the well-formed 3 pairs of parentheses. So a pair of parentheses we can see here is like this. So this is one pair of parentheses. One pair of parentheses consists of one open bracket and one closing bracket, right? So if I have 3 pairs of parentheses, that means I'm given like 3 of these parentheses. And we can see that this means that we have 3 open brackets and 3 closing brackets. So we have a combination of 6 brackets in total. And they want us to generate all possible permutations, all possible combinations involving 3 pairs of parentheses, such that the combinations are all valid. So a valid or well-formed parentheses meaning that like this will be a well-formed parentheses. However, this is not a well-formed parentheses, right? Like this. Because we can see that this closing bracket is not closing any currently open bracket before it, right? So that's just what it means by well-formed. So we can see that this is a well-formed parentheses, right? This is well-formed parentheses, this is well-formed, and so all of these are well-formed. So actually, how do we determine if a bracket is well-formed? If we have a closing bracket, this closing bracket must be closing an open bracket before it. If I have no open bracket and I try to close it, this entire string is immediately invalid, right? And the thing is, I can add as many opening brackets as long as the opening bracket numbers are less than the whatever is available. So if I have 3 pairs of parentheses, I can maximum only have 3 open brackets. Because the moment I have 4 open brackets, this is no longer 3 pairs of parentheses. So let's talk about LeetCode strategies, right? Whenever we want to generate all combinations, like for any questions, if you see the term generate all combinations, or we see terms like find all permutations, this should immediately ring a bell in your head thinking backtracking. When you see this kind of generate all thing, right, the first thing you should think of is backtracking. Why? Backtracking is all about recursively making decisions, right? Because think about it, how do you want to generate all these because there's no like really patterns that we can see that we can go and algorithmically go and generate the thing. It's all about decisions, right? So let's say we start off with an empty string. So an empty string, right? For each decision, right, we can make 2 decisions. Whether we want to add an open bracket, so we add an open bracket to the string, or we add a closing bracket, right? So we can see that for each decision, we can think, okay, now we got this string, right? Can I add an opening bracket to it, or can I add a closing bracket to it? And then for this string, we see, can I actually add an open bracket to it, or can I add a closing bracket to it, right? So we can see that the recursive decision as we go down the tree, right? So this is why backtracking comes in handy. So backtracking is basically, we're gonna go through each state, right? So a state is basically a state of the string. So this is the state of the string, this is the state of the string. And for each state, we are making a recursive call of whether we can make a decision, a left decision or right decision. So the validity of the solution, the validity of each decision is governed by 2 rules in this context, right? So we can only add an open bracket if the number of open brackets are less than k, which in this case is 3, right? So in this point, we can add an open bracket if the number of open brackets is less than 3. So in this case, like we have 0 open brackets and 0 closing brackets in this empty string, right? So in this case, the first decision is valid. That's why we can add an open bracket to it. However, the second thing is we can only add a closed bracket if the number of closing brackets is less than the number of open brackets, right? So in this case, we have 0 open brackets and 0 closing brackets. Therefore, this second statement actually does not come true because we have the same number of closing brackets and opening brackets. If we add this closing bracket, we are not really closing any currently open brackets. So we can see that this string is invalid already. It's no longer well-formed. No matter how many strings, how many brackets we add after this, right? We can add like how many brackets we want. The string is never going to be valid. It's never going to be well-formed. Therefore, we can say that this entire branch is not valid and we can be just ignore it. So for each state of the tree, right, we're gonna ask these 2 questions. Can I add an open bracket? Can I add a closing bracket? And we will follow these 2 rules. And basically we're gonna keep going down all the way down. So maybe you can imagine like we go down the state, making decisions. And at the end, when do we actually stop this recursive function? We stop when the number of characters here is equal to 6, right? So how do we get this 6? It's just basically the pairs of brackets, right? So when we get to the string where it has 3 open brackets and 3 closing brackets, we have a total number of characters is 6, right? We know that the function can stop and we can just go and return the string and add it to the output. Yeah. So let me just go and demonstrate and draw out the entire recursive backtracking state diagram so that we can actually go and visualize how it looks like. So at first, we're going to start with an empty string. We're going to make a first decision. Can I add an open bracket? In this case, yes, I can add an open bracket because the number of open brackets is less than k. So I'm going to add an open bracket. And in this case, I cannot add a closing bracket because I have the same number of open and close, so the second statement does not come true. Right? So in that case, I'm going to go and ask the question here again. Can I add an opening bracket? In this case, I can, right? Because I only have one open bracket, right? So I'm going to add an open bracket here. And then I'm going to ask, can I add a closing bracket? In this case, I can, because I have one open and 0 close. So the number of closing bracket is less than the number of open brackets, right? So what I'm going to do is I can add a closing bracket to it. And so the string is now like this. So for each of these string, we're going to call the function again, call the backtracking call again, and then we're going to make the decision. For this string, can I add an open bracket? Yes, I can, right? Because I still only have 2 open brackets, and 2 is still less than 3, right? 2 is less than 3. Therefore, I can go and add an opening bracket, and then I ask, can I add a closing bracket here? Yes, I can, because I have 2 open and 0 closing. So I can do that. So I'm going to do add a closing brackets to it. So now the string is like this. And for this 3 here, we're going to ask the question again. Can I add an open bracket? Yes, I can. So I'm going to do add an open. Can I add a closing bracket? In this case, I cannot because I have 1 open and 1 close. And so the number of open is equals to the number of close. Therefore, if I were to add a closing bracket, whatever down here is gonna be well formed. So there's no point going to add that closing bracket. So now we have these 3 subtrees, subtrees, right? We can now go and recursively call the function again. So, can I add an open bracket to this? In this case, I cannot because I did have 3 open brackets, right? So if I add one more, it's not going to be well formed. So, but if I cannot add an open bracket, I can at least add a closing bracket, right? So this will become 3 open and 1 close. And then for here, can I add an open bracket? Yes, I can, right? So I can do 1, 2, 3 and add an open bracket. Can I add a closing bracket here? I can also because I have 2 open and 1 close. So I'm going to do open, close, close. And for this leave node, can I add an open bracket? Yes, I can, right? Because I only have 2 open brackets here, right? So I'm going to add a open bracket. And then can I add a closing bracket here? I can also. So I'm going to add open, close, open, close. So we have now these 5 leave nodes. We're going to ask, can I add an open bracket here? I cannot, but I can add a close bracket. So it will become 3 open, 2 close. Can I add an open bracket here? No, I cannot because I did have 3 open, right? But I can add a closing bracket. So this string will become open, open, close, open, close. Can I add an opening bracket here? Yes, I can actually because I only have 2 open brackets. So I'm going to add an opening bracket here. Can I add an opening bracket here? I cannot because I did have 3 open brackets. So this will become just open, close, open, open, close. So I added a close bracket here. Can I add an open bracket here? I can. So this is open, close, open, close, open. Can I add a closing bracket here? I cannot because I have 2 open and 2 close, right? So this will not be well formed. And at last, we're going to try to see, can I add an open bracket here? I cannot, but I'm going to add a closing bracket. So it's going to be open, 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 close, close, close. Then we're going to do here, add a closing bracket. So it's open, open, close, close. And then lastly here, I can add the last closing bracket, open, open, close, close, open, close. Lastly here, I'm going to add my last closing bracket, open, close, open, open, close, close. And the last thing here also, open, close, open, close, open, close. So at this point, we have reached the base case, meaning that, look, we have 6 characters in the string. That means we have used up all our brackets and we can return the function and we can just add the last string here to the output. So we are guaranteed that whatever is at the bottom here is well formed. We can see that these are exactly 5 brackets that they actually want us to return. So let's take a look at how we can write the backtracking function. So when we talk about backtracking, right, this is the easiest problem because once you get the structure and memorize the structure of how we to format the backtracking code, it's all going to be standard. So the standard thing is basically you want to keep the output array, right? So this output array is actually going to be this big array that stores all output strings. So the first step of the skeleton of a backtrack solution is to define the backtrack function within the big function. So this backtrack is actually going to be the recursive function. It's going to take in the output, right? It's going to take in the output array. It's also going to take in the current string. It's going to take in the number of open brackets and the number of closing brackets, right? And obviously, when we have a recursive function, it's important to go and define your base case. So what is the base case? The base case is if the length of the current string is equals to n times 2. So if I have 3 pairs, the base case is when it equals to 6. So if in this case, the base case, we want to return. So when we can see that it equals to 6, right, length 6, it also means that this is now a well-formed string. So we actually want to do output.append the current string. So this means that we have reached the base case. So we got this string. We just want to add it to the big output array such that at the end of everything we can return it. So this is the base case, right? So once we got the base case, now this is where we actually make the decision part. So we want to check, am I able to add an open bracket? So how do I check if I'm able to add an open bracket? It's easy. We just check if the number of open brackets is less than n. If the number of open brackets is less than n, meaning we fulfill the first condition here, so we can do backtrack. So we can call the backtrack recursively, passing the same output array, because we want the big output array, right? This is the global variable that stores all our answers. So we're going to pass in the current string plus the open bracket, right? So basically, here we make a decision where we add this open bracket to the current string, and obviously we want to pass in the same number of open, but we increment it by 1 since we added this open bracket to it, right? But we still have the same number of closing brackets, right? So the second condition is if the closing brackets is less than if num close is less than the num open, right? In that case, we can also make the same decision where we want to backtrack, pass in the output. But in this case, we want to pass in the current string to be a closing bracket. So we want to add a closing bracket to it, right? So the num open is going to be the same, but the number of closing brackets will be incremented by 1. So this is the 2 decisions trees that we make. And then at the end, this is all. We can just call the backtrack function. So what do we pass in? We pass in the original output. We pass in an empty string as a current open string. We pass in the 0 number of open brackets and 0 number of closing brackets. And then at the end, we just want to return the output. So let's think about the call stack of what is going to happen. When we call a backtrack output empty string 0, 0, here's basically what we're saying is we're going to start with this empty string. And then we're going to go in the function, we're going to check, have we reached our base case? Not yet, right? Because it's just an empty string. Then we can make the decision, is the number of open less than n? In this case, yes, right? Therefore, here we're actually making this decision of going left. So we're going to add the current string plus this open bracket. So meaning we're going to add this open bracket to this. And then we're going to go and call this backtrack function again using this current string. So what it's going to do is, from this part, I'm going to go and recursively call. So I'm going to go back to this backtrack again. We're going to check that the end condition is not yet met. However, here, we're going to make this decision. If the number open is less than n, in that case, yes, right? So we're going to add this open bracket to the current string. So we're going to see that it keeps going down, going down, going down, going down, going down, until it reaches the base case. Then it reaches the base case, it adds the current string, which is, it adds this to the output, right? And then it returns, and then it gets popped all the way back up here to the original thing here, and then now it goes to the second condition. So that's how the recursive backtracking solution will work to generate all the parentheses. So let's try submitting this code, and we can see that it runs really fast. It beats 97.48%. So the space complexity in this case is gonna be O of n times 2, right? Which is actually basically O of n. So it's a linear solution. Why? Because we can see that the space complexity just requires us to keep track of the depth of the tree, right? And you see the depth of the tree goes all the way until just n over 2. Because the height here is going to be n times 2, right? Because at the end, the base case here is just going to be the length of all the strings, all the brackets. So yeah, that's the space complexity. So I hope that this backtracking solution has helped you better understand recursive functions and how to generate all possible parentheses. Thank you for watching.